Hi everyone, Dr. Burns here with our second lesson in Chapter 8, Chemical Reactions, where we're going to be learning about limiting reactants. Now, limiting reactants, the problems that we're going to be doing are extensions of what we learned in our previous lesson where we talked about chemical equations and using calculations with balanced chemical equations. So we're going to use what we learned previously to learn about limiting reactants. So, we've talked about chemical reactions, and we said that a chemical reaction is started only when the reactants come into contact. Okay, so we can write out our chemical reactions and we can balance them, but they don't actually start until we mix our reactants together. Think of this like when we mix vinegar and baking soda together before they bubble up. Okay, when I have vinegar by itself and baking soda by itself, neither of those are reacting. So they have to come into contact with each other to start the reaction. But what determines when the reaction finishes? Okay, how do we know when the reaction is going to be done? What controls that? So let's think about a balanced reaction. So here we have the formation of carbon dioxide, where I take carbon monoxide and react it with gaseous oxygen and create carbon dioxide. So from our balanced equation, we know that if I take 2 moles or 2 molecules of carbon monoxide and I react it with 1 mole or 1 molecule of oxygen gas, I create 2 moles of carbon dioxide or 2 molecules of carbon dioxide. So once I've used up 2 moles of CO and 1 mole of O2, then my reaction finishes because I've created 2 moles of carbon dioxide. Okay, so once I've used up all of those reactants is when my reaction is done. But if we're thinking of the real world, if we're chemists, we're thinking in a lab setting, our reactants are usually not present in perfect stoichiometric amounts. Okay, when we're making a volcano with vinegar and baking soda, we just dump baking soda in there and pour enough vinegar till we start to see bubbles. But sometimes we have baking soda left over because we didn't measure exactly perfect amounts for those to be reacting completely. So this suggests that one reactant may be completely used up while another will have some left over. The reactant that's used up first in the reaction is the limiting reactant because that limits the chemical reaction, how far the chemical reaction can go and how much product we can create. So it is what limits the reaction. The excess reactant, or reactants if there's multiple, are those present in quantities greater than necessary to react with the quantity of the limiting reactant. So it's whatever is left over. So in our example, we have a lot of excess baking soda, and our limiting reactant was the vinegar. So I've used up all of that vinegar to make my bubbles and make my volcano, but I have some extra baking soda left over that's unreacted. So what do? We keep adding our vinegar. So I have a few real-life examples of limiting reactants. One of those is making s'mores. Okay, right now I'm in the summer, so this is peak s'more making time. And when we're making s'mores, we always somehow end up with a lot of graham crackers left over, and we usually run out of chocolate first. Okay, and that just depends on how much we buy of each. When we buy a box of graham crackers, there's enough graham crackers to make about 20 to 30 s'mores. When we buy a bag of marshmallows, there's usually just about enough to make that many as well. But when we buy chocolate, if we don't buy enough, then we can't make as many s'mores because a s'more without chocolate is just disgusting. So we can say that whatever piece of the s'more that we have in lesser quantity is going to limit the number of s'mores that we can make. And that's why we always end up with graham crackers left in our pantry that just end up going bad because we're sitting there eating most of the chocolate anyways. Another good example of this is hot dogs. Do you ever notice how hot dogs are sold in packages of 10, but the buns come in packages of 8? That doesn't make any sense. The buns are going to limit the number of hot dogs that we can make, a good hot dog where we have a bun and a hot dog in it. So in chemistry, we see the buns as the limiting reactant. Okay, so our equation would look like this. We have 10 hot dogs and only 8 buns, so I can only make 8 good hot dogs, and I'll have 2 bunless hot dogs left over. Okay, so we usually end up not eating those anyways. So before we jump into how this relates to chemistry, let's just think of what a limiting reactant is in terms of a chemical equation, or an equation at all. We won't even say it's a chemical equation. So consider this reaction. 2A plus B goes to C. In the diagram here that represents this reaction, which reactant, A or B, is limiting reactant? So the limiting reactant would be the one that's used up first. So we know that 2A molecules, oops, that's B, sorry, 2A molecules combine with a B molecule in order to create our product of C. So what we can do is start pairing up our molecules here to see what's left over. So I have 2A's with a B, 2A's with a B, I have 2A's with a B, and then I have an A with a B. So I can make 1, 2, 3, 4 C's from all of the A's and B's that I have, and what I have left over is a B. So what's left over, that's my excess. So B is my excess, therefore my limiting reactant is A. Because I used up all of my A molecules, my green molecules, I used them all up, I couldn't do anything with my extra B molecule. So I have excess B left over because my reaction was limited by my reactant A. Okay, a similar problem. Reactants A and B. A is red, B is blue. Combine in the reaction vessel shown to form a single product C. According to the equation 2A plus B goes to C, which of the following scenes represents the contents of the reaction vessel after the reaction is complete? Well, this is similar to what we did before, we just have a slight change in color. So we know that 2 A's are going to combine with a B, so B is blue, A is red. So what I want you to do is pause your video and make up your C molecules by connecting A's and B's in the correct proportions, and try to find which of these products or which of these options would be what the reaction vessel looks like after the reaction is complete. If we keep going with our circling, we have 2 A's mixed with a B. We have 2 A's that can mix with a B. We can have 2 A's that mix with a B. So when these combine, they're going to turn into purple, which is C. We would have 1, 2, 3, 4 purples, and what's left over is a blue. So we have 1 blue left, which was B. So this suggests that B is excess, A is limiting, and our product or the reaction vessel after the reaction is complete should have 4 purple dots and 1 blue dot. Well, our first example here, A, just has all purple dots and far too many of them, so that one's wrong. B has a lot of purple dots and 1 blue dot, but it has too many purple dots. Okay, remember these A's and B's are combining to make one single product. Okay, it's a combination reaction. So we have too many purples here, so that's wrong. C is looking like a good answer. We have 1, 2, 3, 4 purples and a blue. And our last two examples have reds as what's being left over, and we know that blue is what's excess, so those would be wrong as well. So our answer would be C. Okay, so let's now consider a chemical process, because that's what we're going to be using this concept for, of limiting reactants, is for chemical processes. So here we have hydrogen gas reacting with chlorine gas, creating hydrogen chloride. So imagine combining 3 moles of hydrogen gas and 2 moles of chlorine gas. When we're doing limiting reactant problems and we have balanced equations, the approach for determining the limiting reactant involves comparing the amount of product expected for the complete reaction of each reactant. So we start off our reaction with 3 moles of H2 and 2 moles of Cl2. Once one of those is used up, that's as much HCl that we can form. So what we can do is use our mole-to-mole ratios to calculate how much HCl would form for each reactant. So the reactant yielding the lesser amount of product is the limiting reactant. So let's look at how we do that. So we started with 3 moles of H2. So for each reactant, we're going to calculate how much HCl we can form. So if we started with 3 moles of hydrogen gas, we can use our balanced equation to convert from moles of hydrogen gas to moles of HCl. Moles of hydrogen gas is in the bottom of our equivalency so that it can cancel, and we're left with moles of HCl. So if I reacted all 3 moles of hydrogen gas, I would get out 6 moles of HCl. We can do the same thing for the 2 moles of Cl2, where we use our mole-to-mole ratio, again putting moles of Cl2 on the bottom to cancel out our units appropriately. And we get out that if we reacted all 2 moles of chlorine gas, we would get out 4 moles of HCl. And our rule for limiting reactants says, well, whatever produces the lesser amount of product is our limiting reactant. Because this is saying that after I use up all 2 moles of my Cl2, the maximum amount of HCl that I can make is 4. Once I've used that up, I can't create any more moles, so I can't get to 6 moles of HCl. So the Cl2 will be consumed once 4 moles of HCl are produced. That means that we have unreacted H2 that will remain once the reaction is complete. This means that Cl2 is the limiting reactant because it produced the lesser amount of product, and H2 is the excess reactant because we're going to have some H2 left over. We can then calculate how much of the excess reactant is left over. So what we can do is convert the minimum mass or mole amount produced by the limiting reactant to the moles of the excess reactant. Then, if needed, we have to convert moles of excess to mass of excess depending on what the problem gives us. And this is the amount of excess reactant used up in the reaction. So we're basically saying I'm going to take the lesser amount of my product, okay, that was produced by my limiting reactant, and I'm going to work backwards and determine how much of my excess reactant I actually used up. Then what we can do is take the difference between the amount of the excess reactant we started with and subtract off the amount of excess that was actually used. So if we relate this back to our hot dog example from earlier, our amount of excess reactant that we started with, well, that would be our hot dogs. We started with 10 of them, but my buns limited the number that I could use, so I only ended up using 8 of those hot dogs because I only had 8 buns. So I only used up a partial amount of those hot dogs. So if we take the difference between those numbers, we know that we have 2 hot dogs left over. So let's do that for our example of hydrogen and chlorine. So we said that the maximum amount of HCl that we can produce is 4 moles. So we start with 4 moles of HCl. And what we want to do is now convert that value back to our excess reactant. So our balanced reaction, if I go back to it, had 2 moles of HCl and 1 mole of H2 gas, remembering that H2 was our excess reactant. So we have 2 moles of HCl for every 1 mole of H2. So to make 4 moles of HCl, I only had to use up 2 moles of H2. I started with 6 moles of H2, so to find my excess left over, we take the 6 moles that we started with. Was it 6 moles? No, 3 moles. I'm sorry, 3 moles. There we go. 3 moles of H2 that we started with, we subtract off the 2 moles of H2 that we used up, meaning I only have 1 mole of H2 left in my reaction, or in my reaction vessel. That is how much is left over, unreacted. So let's keep practicing this. How many moles of water could be made from 5 moles of H2 and 3 moles of O2? So I have the balanced reaction here, and we're saying if I'm mixing together 5 moles of hydrogen gas and 3 moles of oxygen gas, what is the maximum amount of water that we can create given that one of these reactants is going to limit us? So what we want to do is start off with our molar values of each reactant. So we're going to start first with 5 moles of H2, and we're going to convert that to our product, our water. So our mole-to-mole ratio for H2 and water is 2 to 2. So I put 2 moles of H2 on the bottom and 2 moles of H2O on the top. That'll cancel out our H2s, and we'll be left with 5 moles of water. Now we go to our 3 moles of oxygen and do a similar conversion. Instead of having moles of hydrogen gas, though, we're going to do 1 mole of oxygen gas for every 2 moles of H2O. And that gives us 3 times 2, which is 6 moles of H2O. So we've taken both of our reactants and determined how much product they could produce if they fully reacted. And whichever one produces the lesser amount of product is then the limiting reactant. So the lesser amount of product is 5 moles of H2O, meaning our limiting reactant is H2. Now remember, this is called limiting reactant. So one of your reactants has to be what's limiting. So sometimes I'll see students that convert it to the product and then say that the product is limiting because they see that value there. Remember, we're dealing with just the reactant. So whatever created that lesser amount of product is what is limiting that reaction overall. So I'm only going to create 5 moles of water because I used up all 5 moles of my hydrogen gas. This means that O2 is excess. Which brings us to our next question. For the same reaction, okay, what is the excess reactant? Well, we just said that that is O2, so we know that our answer is going to be one of these two. And how much of it is left over? So we said that the maximum amount of water that we can make is 5 moles. So we start off with 5 moles of H2O. And we want to convert that now to our excess reactant. So I want to convert it back to O2 to see how much O2 I actually needed to create that amount of water. So we're going to use our mole to mole ratio. We have 2 moles of water on the bottom because we're canceling it out. We have 1 mole of oxygen in the top because that's our excess. So 5 divided by 2 is 2.5 moles of oxygen gas. So I only needed to use 2.5 moles of oxygen to create those 5 moles of water. So that's how much we needed to use up. But I want to know how much is left over. So this is used up. So our original problem says, well, I started with 3.0 moles of oxygen and I used up 2.5 moles of oxygen. So how much is left over? Well, it's the difference of those two. So we take 3.0 moles of oxygen and subtract off the 2.5 moles of oxygen that we used, and we have 0.5 moles of oxygen left over. So our answer for this would be B. Now I want to show you another way of doing this problem that gets us the same answer. It just does it in a reverse order. So, and I oftentimes see students doing it this way as well, just because it makes more sense in their brains as opposed to the other way. So there are multiple ways that you can solve these types of problems. I believe your textbook does show a different way. So what we can do to find the amount of excess left over is we can take these two amounts of our product and we can find the difference between those, because that's basically saying, well, here's how much I could have made and here's how much I actually made. The difference is then going to be related to the excess reactant. So what we can do is take that 5.0 moles and subtract off the 6.0 moles. We'll take that absolute value because we can't have a negative mole value. Okay, and we get that the difference between them is 1.0 moles of H2O. We can then take that difference value and convert that to our excess reactant in order to see how much was unused in the reaction. So we take 1 mole of water, we do our mole to mole ratio, so I have 1 mole of O2 on the top and 2 moles of H2O on the bottom. Again, that comes from my balanced reaction. And 1 divided by 2 is 0.5 moles. Oops, not H2O, of O2. So that again gets us the same answer. It's doing the same steps, just in reverse. So in the previous version, I found the moles of excess and then I subtracted. Here I did my subtraction first and then converted to moles. It's the same concept, but sometimes our brains just think about it differently and see the concept differently. And those are the two ways that you can visualize this concept, at least through the math. And the best way to learn this is, again, through practice. And if you haven't noticed that from our lectures so far, we love to practice because that does show us how to do all these problems over and over again. So let's keep practicing. Our next problem says nitric oxide reacts with oxygen gas to form nitrogen dioxide. In one experiment, 0.885 moles of NO is mixed with 0.514 moles of O2. Determine which of the two reactants is the limiting reactant. Calculate also the number of moles of NO2 produced. So we're going to set up a similar problem here as we did with our previous examples, where we're going to take our moles of each reactant and convert it to moles of product. And we have the balanced reaction already. So we're just going to start with each reactant and convert it to our product of NO2. So we start with 0.885 moles of NO, and we convert that to moles of NO2. So I put moles of NO on the bottom so that it cancels, moles of NO2 on the top so that I have that unit left. I go to my balanced reaction and see that both of those values have a coefficient of 2, so this would be a 2 to 2 ratio. So we get moles of NO2 to be 0.885 moles of NO2. We then go to our other reactant of O2, which starts off with 0.514 moles of O2, and we now use our ratio to convert that as well. So we put moles of NO2 on top, moles of O2 on the bottom so that it cancels. We know our coefficient for NO2 is 2, and our coefficient for oxygen gas is 1. So we're going to take 0.514 and multiply that by 2. So we get 1.028 moles of NO2. So we look at our two values for our products, and the lesser of the two is what's limiting. So the lesser amount was 0.885 moles of NO2. That was created by NO, nitric oxide. So NO is limiting. Then it says also calculate the number of moles of NO2 produced, which we already did through this process. Now your textbook does show a different way, and I believe Alex shows this way as well, but there are multiple ways to do these problems. I personally find going from reactant to product the easiest way because most of these questions are usually asking for how much product is produced, so this is a direct way. Your textbook does show a way where you go from reactant to reactant, so you go from moles of NO to moles of O2, and then in your second reaction, moles of O2 to moles of NO. And this basically tells you the moles of each reactant that are needed to complete the reaction, and whichever one you don't have enough of is then your limiting reactant. I personally find this a very roundabout way of finding the limiting reactant because the next step after this is then to convert to your product, which again is just an extra step that's not needed when you can go directly from each reactant to product, and that also tells you the limiting reactant because they're all coming from the same balanced equation. So just keep that in mind as you're doing your practice through your textbook or in Alex, as it may show a different way where it's going from reactant to reactant, and that is a totally acceptable way to do these problems. But the way that I'm showing it as well, where we go from reactant to product, is equally as acceptable and gets us to the same numbers because all it's doing is using our multiple ratios in the same way. Okay, since they're all coming from the same balanced reaction, the ratios work out the same way. Okay, so there are multiple ways that we can figure out these problems. Okay, let's keep practicing. So, what I want you to do is I want you to pause your own video and try these problems on your own. Now, the first thing you're going to have to do for each of these is write out the balanced reactions. We don't have the balanced reactions for these two problems, so you're going to have to write them out first. So again, we have to make sure we're mastering balancing chemical equations, because if we don't have the correctly balanced equation, then we don't have the correct ratios. And if we don't have the correct ratios, then we don't get the correct product. Okay, so we need to make sure we can balance these equations first and then use those ratios to find our limiting reactant. So pause your video take some time to go through these two problems, write out their balanced reactions, and try to figure out their limiting reactants. Our first example, the balanced equation, is a combustion reaction. So the balanced equation comes out to 2C2H2 plus 5O2 goes to 4CO2 plus 2H2O. Now this reaction, you would have to use an intermediate fraction like we saw in our previous lesson. So that's how we were able to get the 5 in front of the O2. So just keep that in mind if you were stuck balancing and got to the oxygen and said, how do I make a 2 into a 5? That's where we can use our intermediates and go from a fraction to a whole number. Okay, so now that we have the balanced chemical equation, we want to find out what the limiting reactant would be. Now for this, we have two products, so what we can do is one of two things. We can convert each reactant to just one product, or we can convert each reactant to both products. Either way you do it, you're still going to find the same results of what's limiting, okay, because of those multiple ratios. They all relate to each other. So let's start out with going from 2 moles of C2H2, and let's convert that to moles of CO2. So we have 2 moles of C2H2 goes to 4 moles of CO2. So we have 2 times 4 divided by 2. So we get out 4 moles of CO2. We can do the same thing with our moles of oxygen. We can do 1.0 moles of O2. For every 5 moles of O2, I get out 4 moles of CO2. So we get 1 times 4 divided by 5, that ratio. So we get out 0.8 moles of CO2. So the lesser amount comes from O2. So we could say that O2 is limiting. Now we can check our work, always good to check our work, and convert it to our other product of water. So we start off again with the same amount of reactant, and now we're going to convert it, instead of CO2, convert it to water. So that's just 2 moles. And then for oxygen, we start again with 1 mole of O2. And for every 5 moles of O2, we get out 2 moles of H2O. So we do 1 times 2 divided by 5. Oops, not 59. There we go. So that gets us out 0.4 moles of H2O. So again, that shows that O2 is limiting. And for this problem, it just asked for the chemical formula, so you would just type in O2. Okay, next up we have solid aluminum and chlorine gas react to form solid aluminum chloride. Suppose you have 11 moles of aluminum and 2 moles of chlorine in a reactor. calculate the largest amount of AlCl3, aluminum chloride, that could be produced. Round your answer to the nearest 0.1. Now, this problem does have some word trickery in there. Because it's a limiting reactant problem, the largest amount of aluminum chloride that can be produced would be the one that produces the lesser number. Okay, so remember that whatever reactant produces the lesser amount of product is then limiting, because that's the maximum amount of product that we can create given our reactants. Okay, so it's a little bit of word trickery in there. So we're going to start this problem out by balancing our chemical equation. So we have Al plus Cl2 goes to AlCl3. To quickly balance this, we would put a 2 in front of the AlCl3 and a 3 in front of the Cl2 to balance out those chlorines. Okay, one has 2, the other has 3. Since there's nothing easy to balance there, we're just going to multiply by those values to get 6. And because we added a 2 in front of the aluminum on the product side, we're going to put a 2 in front of the aluminum on the reactant side. So, again, the importance of a balanced reaction. If we didn't balance it, then we wouldn't have any multiple ratios. It would all be 1-to-1, which would not be correct. So we have to have the balanced equation first. So now that we have the balanced equation, we can use our values that we're starting out with. So we have 11 moles of aluminum that we're going to convert to aluminum chloride through our multiple ratio. So 2 moles of aluminum goes to 2 moles of AlCl3, aluminum chloride. So we get out 11 moles of aluminum chloride. We then do our next reactant, which is 2 moles of Cl2. And we use our multiple ratio, which is for every 3 moles of Cl2 used, we create 2 moles of aluminum chloride. So we take 2 times 2/3, and we get out 1.33 moles of aluminum chloride. So, because based off of our reactants, the amount of reactants that we have, the maximum amount or the largest amount of aluminum chloride that we can produce from this reaction is 1.33 moles. Okay, it's not 11 moles because I don't have enough chlorine to produce that much aluminum chloride. So since the chlorine is limiting us, I can only create 1.33 moles of aluminum chloride. So my answer for this, rounded to the nearest 0.1 mole, would be 1.3 moles of aluminum chloride. So don't let the word trickery here change how you think about these limiting reactant problems. Okay, now let's pause and try this one. This one is similar to all of our previous examples, except now I'm bringing in mass, and I want to get out mass. Now this is no different from what we've been doing in previous sections, previous lessons, going from grams to moles. We know how to do that. We've been doing that for multiple chapters now. Okay, so the first thing that we're going to want to do is, instead of going right into our multiple ratio to compare our reactants to our products, we first want to convert grams to moles so that we can properly use our multiple ratio. So the first thing we're going to do is we're going to start with the 48.2 grams of HCl, and we're going to convert that to moles. So we're going to use the molar mass of HCl, so 1 mole of HCl is equal to 36.46 grams, and again, I'm just getting that from the periodic table. So we take 48.2 and we divide that by 36.46. and that gets us out 1.32199 moles of HCl. So I now have my moles of one reactant. The problem also gives us 0.86 moles of our other reactant, MnO2. So now what we want to do is determine the limiting reactant, the reactant that will be used up first, and then we want to find the number of grams of Cl2 that will be produced from that limiting reactant. So we've set up the problem to start off just like our previous examples, so pause your video and complete this problem. So we have our mole values of each of our reactants in a balanced chemical equation, so we can convert from moles of reactant to moles of product. So we have moles of HCl and we want to get out Cl2. That's what our question is asking us for. You could have gone to any reactant, okay? You could have gone from Cl to MnCl or to water. It doesn't matter. But since the problem is specifically asking for the mass of chlorine that will be produced, it's just good practice to do your first conversion to the product that the question is asking for. But again, like we saw in our previous examples, you can go to either product, any product, and it'll still tell you what's limiting. So we're going to convert this from 4 moles of HCl to 1 mole of Cl2. So we get this divided by 4, right? And we get 0.3305 moles of Cl2. For MnO2, I have a 1 mole MnO2 for 1 mole of Cl2. So we get out 0.86 moles of Cl2. So this suggests that because this is the lower amount, HCl is limiting. So that answers our first question of which reactant will be used up first. HCl is our limiting reactant, and that will be used up first. The second question is now asking for the grams of chlorine that will be produced. Well, we have moles of chlorine, so we can start off with that 0.3305 moles of Cl2, and we can convert that to mass. So we have that in 1 mole of Cl2, we have how many grams? Well, the molar mass of chlorine is 35.45. We're going to multiply that by 2 because this is diatomic. So it's 70.90 grams. So we'll take that 70.90, multiply it by 0.3305, and we get out 23.43245 grams of Cl2 that will be produced. Now for sig figs, because we did not use the mole value of MnO2 to determine our mass of chlorine, I went from 48.2 to find this answer. We would actually only consider the 48.2 as our significant figures value. So this would actually come out to be 23.4 grams of Cl2. So the MnO2 did not contribute to calculating the mass of chlorine that was produced because that's our excess reactant. So its value does not come into play in the significant figures determination because its number was not used to find the final value. Okay, so now that we know how to find our maximum amount of product that we can create given a certain amount of reactants, we can now utilize that to determine a reaction yield. So we have 3 different yields to talk about. The theoretical yield of a chemical reaction is the amount of product that forms when all of the limiting reactant reacts to form the desired product. We talk about the theoretical yield as being the perfect world example. Everything in the reaction goes perfectly. I use up all of my limiting reactant. Nothing gets in the way. The temperature, the pressure, everything about those experimental pieces is perfect. And that's the maximum amount of my product that I can create. We then have the actual yield of the chemical reaction, which is the amount of product actually obtained from a reaction. So in a lab setting, we are not in a perfect world. We have things that are going to affect our chemical reactions from happening. Maybe we didn't measure out our reactants perfectly. Maybe there is a slight contamination. Maybe when we were heating this reaction up to react it further, we didn't get to the desired temperature. There are many things in the real world that can affect a chemical reaction. And this is what plagues chemists all day, every day, is figuring out how good of a yield they can get from their chemical reaction. So this is the real world example. So our actual yield and our theoretical yield are very rarely the same because it's very hard to get to perfectly the theoretical yield amount of our product. So the comparison of the actual yield and the theoretical yield is called the percent yield. And that tells us what percentage the actual yield is of the theoretical yield. The higher the percentage is, the percent yield is, the closer our actual yield is to our theoretical yield. Think of it like a test. Okay, we want to get 100 points. Our actual yield is however many points we actually get. Okay, the closer we are to that theoretical yield value, to in this case 100 points, the better our yield is going to be and the better the reaction was. Okay, so a high yield, a high percent is good. A low yield, a low percent is bad. Okay, so let's look at a few examples of this. What is the percent yield of a reaction that produces 12.5 grams of the gas CF2Cl2 when 32.9 grams of CCl4 reacts with excess HF? Now there are a lot of words and a lot of numbers in that problem, and we have to decipher what each of them are. So we want to know the percent yield, that's what we're looking for. And we know that this reaction produces 12.5 grams of CF2Cl2, which is one of our products. So because we know how much this reaction yields, this is the actual yield. That's how much we know we can get out from this reaction in the real world. That's our real world example. So we want to know what the percent yield is if I start off this reaction with 32.9 grams of carbon tetrachloride, CCl4. Now I tell you that this is excess HF, so the excess doesn't matter because we know our limiting reactant is what's controlling the amount of product we can make. So the HF doesn't matter. We don't care about it. It's there, there's enough of it to react fully, so it doesn't matter. The only thing that's going to affect the amount of product is going to be the carbon tetrachloride, CCl4. So the first thing we want to do is determine the theoretical yield. So we want to take this mass of CCl4 and convert it to a mass of our product. Okay, because we know that that's the maximum amount of product we can make from the limiting reactant. once we find that theoretical yield, we're going to compare it to our actual yield using our equation, actual over theoretical multiplied by 100. So our first step is to determine the theoretical yield. So we start off with our mass of CCl4, 32.9 grams of CCl4. And we're going to convert it to moles. Why are we converting it to moles? Because I need to change it from one chemical species to another. I need to convert from a reactant to a product. And the only way to do that is through a mole-to-mole ratio. So I need to convert my mass of my reactant to moles so that I can use the mole-to-mole ratio to go from reactant to product. Okay, so we need to know our molar mass of carbon tetrachloride. So we get 12.01 plus 35.45 times 4. We get 153.81. So we get 153.81 grams is 1 mole. So we take that, we do 32.9 and divide it by that value. Okay, so we have 0.2139 moles of CCl4. Okay, so we're going to start there now, 0.2139, I can probably zoom in a little bit here, moles of CCl4. And we want to convert that to our moles of our product, which is going to be CF2Cl2, because that's the mass of the product that we have. Okay, so we're going to go to that product. We see it's in a 1-to-1 ratio. So we have 1 mole of CF2Cl2 and 1 mole of CCl4. So we get out 0.2139 moles of CF2Cl2. Now I can't compare that mole value to this mass value to find my yield because they're not in the same unit. So our percent yield has to be the same units. So the only way to do that is to convert this moles to grams. So we're going to take that 0.2139 moles of CF2Cl2 and convert that to mass. So 1 mole of CF2Cl2 has a molar mass of 120.91 grams. Okay, so we take that value of moles, we multiply it by 120.91, and we get 25.9 grams of CF2Cl2. Okay, so this right here, that 25.9, that's our theoretical yield. So we now have our actual yield up here and our theoretical yield. We have those values and they're in the same units. So now we just have to plug them in to our percent yield equation where we take the actual and divide it by the theoretical and multiply by 100. We just have to do that division to find our yield. So we take the 12.5 grams, that's our actual yield, and we divide it by the 25.9 grams and multiply by 100. So we take 12.5, divide it by 25.9, we multiply that by 100. And we get a percent yield of 48.3%. 3 sig figs because of our original problem having 3 sig figs. So that is our percent yield, 48.3%. So I only produced about half the amount of product I would expect to from this reaction. Okay, let's do another one. So a similar problem where I give you grams of a reactant and a product. We want to find the percent yield. The only thing is we don't have a balanced reaction yet. So the first thing that we're going to want to do is write out our balanced reaction. And we can't do that quite yet because this problem is missing one thing. So I've got out copper metal and zinc 2 sulfate. So the product of my reaction between copper 2 sulfate and excess zinc was copper metal and zinc 2 sulfate. So you can use that to write out your balanced chemical reaction. So do that now. Our balanced chemical reaction is balanced as we write it. Everything's in a 1-to-1 ratio, so we get copper sulfate. Copper 2 sulfate is CuSO4. They have equal but opposite charges. Plus zinc metal, which if it's in its metal state, then it has a charge of 0, so it's by itself. Then we get copper metal out plus zinc 2 sulfate, which is ZnSO4. So that's everything's in a 1-to-1 ratio. The next thing we want to do is complete this problem similar to how we did the last problem. We want to determine the theoretical yield from our mass of reactant and then compare that to the actual yield, which is given here as 0.392 grams of copper. So this is our theoretical yield because it's the product that we're getting out. So we know that copper 2 sulfate is our limiting reactant because the product says that we have excess zinc. So the only thing that's controlling the amount of product that we're getting out is the copper 2 sulfate. So we're going to start this problem off by taking the mass of copper 2 sulfate, that 1.274 grams, and we're going to convert that to moles. So in 1 mole of CuSO4, that has a molar mass of 159.61 grams. So we get out for that 1.274 divided by 159.61, and we get moles of 0.0079819 moles of CuSO4. We now want to convert that to moles of our product, which is copper. So for every 1 mole of copper sulfate, we get out 1 mole of copper solid. So this leaves us with 0.0079819 moles of copper. Now our actual yield is in units of grams, so I would need to convert my moles of copper to grams of copper so that they are in the same unit. You technically could also convert this grams of copper to moles of copper and then compare those. As long as they are in the same units, they're going to give you the same yield. So we know our molar mass of copper from our periodic table. It's right there as 63.55 grams. It's from the periodic table. So we take that 0.007 and we multiply it by 63.55 and we get out 0.507 grams of copper. Okay, so that's our theoretical yield. So if all of my copper sulfate reacts perfectly, I should get out 0.507 grams of copper. But we know from this reaction that we only get out 0.392 grams of copper, so we can find the percent yield by taking that actual amount, that 0.392, and dividing it by the theoretical, 0.507 and multiplying it by 100. So we take 0.392, divide that by 0.507, and then we multiply that by 100. So we get a percent yield of 77.3%. And that's how much we yielded from this reaction. So we didn't get a perfect reaction because we are not in a perfect world, but we got a good amount of our product out from this reaction. A good rule of thumb to make sure you're on the right track, we would rarely have a percent yield that's going to be higher than 100. So percent yield should be lower than 100%. Okay, so that's always a good one, which means that our actual value is always going to be lower in amount than our theoretical. The number of from the actual compared to the theoretical, actual will always be lower than the theoretical value in order to get a percentage of less than 100%. Now, in the actual real world, in a real chemistry lab, for amateur chemists in general chemistry labs, sometimes we get percent yields that are higher than 100, and that just comes down to contamination issues. Maybe our product wasn't dry or anything like that. So it is possible to have a percent yield that is higher than 100%, but in these kind of generated problems from our textbook, we would rarely see a percent yield that is higher than 100%, unless it clearly says there was a contamination in the student's lab. What is the percent yield from this contamination? And that would be higher than 100%. So most of the time you're going to see a percent that's lower than 100. If you have a percent that's higher than 100 or something that's really, really small, then you did something wrong and you're going to want to double check your work. Okay. What I want you to do now is try this problem completely on your own. So we have a very similar setup to our previous problems. I give you the balanced equation. I give you the masses of what we're starting with and what our yield is. So we have our starting product of calcium fluoride and our actual yield of HF. We want to find the percent yield of HF. So follow the same steps that we've done in our previous problems in order to find the percent yield for this specific problem. The first thing we're going to want to do is convert our 6 kilograms of calcium fluoride to grams. So 6 kilograms converts to grams by multiplying by 1,000, because there are a lot of grams in 1 kilogram. So we get this to be 6,000 grams of calcium fluoride. Once we have grams, we can use the molar mass to convert to moles. So in 1 mole of calcium fluoride, we have 78.08 grams. And we get out from this 6,000 divided by 78.08. So we get 76.844 moles of calcium fluoride. Okay, so now we have to take that moles of calcium fluoride and convert it to HF. So we're going to take 76.844 moles of CaF2, and we are going to convert it to HF. So for every 1 mole of calcium fluoride, we get out 2 moles of HF. So we take that 76 and we multiply it by 2. And we get out 153.688 moles of HF. Our actual yield is in kilograms of HF, so we're going to want to convert this mole value of HF to kilograms. And the first step to do that is to take that 153.688 and use the molar mass to convert. That is 20.01 grams. And we get 3,075.307 grams of HF. And to convert it back to kilograms, we just divide by 1,000. So we get grams to be, or kilograms to be 3.0753 kilograms. We can round that off to 3.08 kilograms for sig figs. And then that's our theoretical yield. Here's our actual yield. We'll just take those two values and compare them. So we take the 2.86 kilograms of HF and divide it by the theoretical 3.08 kilograms and multiply by 100. We get a yield of 92.9%. There we go. Okay, on to another one. Here's another one that you should try on your own first before we go into it. A very similar setup to our previous examples. We're starting with kilograms again. So we're going to have to convert to grams and then to moles. So keep that in mind. So try this problem on your own and come back to check your work. So we're given our balanced reaction here. So the only thing that we have to do is convert from kilograms to grams of our reactant, and then from grams to moles, so that we can go between moles of our reactant to moles of product, so that we can compare to our actual yield. So we're going to start out with 8.0 times 10 to the 3 kilograms of this ilmenite, FeTiO3, and we're going to multiply by 1,000 to go from kilograms to grams. So that gives us 8.0 times 10 to the 6 grams. We can then use the molar mass of ilmenite in order to find the moles. So in 1 mole, it has a molar mass of 151.71 grams. So we take 8.0 times 10 to the 6, we divide it by 151.71, and we get a mole value of 52,732.186 moles of FeTiO3. We now want to convert from our reactant to our product, and that's all in a 1-to-1 mole ratio. I think everything in this reaction is a 1-to-1 mole ratio. So our product out of TiO2, titanium oxide, is also 52,732.186 moles. Okay, so our actual yield is in units of kilograms, so we're going to take that 52,732 and we are going to convert it from moles to grams using the molar mass. So 1 mole of TiO2, that's a 2, is 79.90 grams. So we'll multiply that by 79.9 and get out 42,13301.69. That's grams. And to convert it to kilograms, we're going to divide by 1,000. So we get our mass out to be, we'll put it into scientific notation, 4.213 times 10 to the third kilograms. And that is going to be our theoretical yield. So our percent yield then is our actual, which is that 3.67 times 10 to the 3 kilograms divided by this 4.213 times 10 to the third kilograms multiplied by 100. So we'll take 3.67 times 10 to the 3 and divide it by our answer there and multiply by 100. And we get a yield of 87.1%. So that's our yield for that reaction, another good reaction, nice and high yield. Okay, let's keep practicing. Let's do another one. This was a problem we already did. I don't know how it got on there twice. I don't believe it's on your lecture packet twice, but if it is, just cross it out. We already did it. Feel free to re-practice it if you want. Okay, so we'll move on to our next one. Ethylene, an important industrial organic chemical, can be prepared by heating hexane at 100 degrees Celsius. If the yield of ethylene production is 42.5%, what mass of hexane must be used to produce 481 grams of ethylene? So this problem's a little bit different than what we've been doing. It requires us to work backwards. We're given the yield and we want to know the mass of our reactant that we need to get that yield. So the numbers were given. This is our percent yield. And that 481 grams is our actual yield. So they know that this reaction is not efficient and it only produces 42% of what it should. So if the desired amount is 481 grams, well, I need to know what that original mass is to get that type of yield. So my actual amount that I want to get is that 481 grams. So we can use that to find our theoretical yield, which we can then use to convert back to our reactant. So if we look at our percent yield equation, we know our percent yield is 42.5%. We know our actual is 481 grams. We don't know our theoretical, and we know we have to multiply this by 100. So we want to solve for our theoretical yield, because if we know the theoretical yield of product, we can convert it back to our limiting reactant. So we'll take this, we'll divide both sides by 100, get 0.425. We'll do a little algebra and say that our theoretical yield is equal to 481 grams divided by 0.425. That's our yield. So we take 481 and divide it by 0.425. So our theoretical yield here is 1,131 grams, 0.76 grams. And that's of ethylene, which is C2H4, which is our product. So now that we know the mass of ethylene, the theoretical mass of ethylene that we need, we can use that to convert back to our reactant of hexane. So we'll take that one, here I'll change colors. We'll take that 1,131 and we will convert that to moles. So 1 mole of ethylene has a molar mass of 28.06 grams. So we divide that by 28.06 and we get 40.33 moles. So 40.33 moles of C2H4 converts with a 1-to-1 ratio to hexane, which is our reactant. So we're converting from here to here. That's all in a 1-to-1 mole ratio. So that's 40.33 moles of hexane, which is C6H14. Now that we know the moles of our limiting reactant, we can convert that to mass of limiting reactant, which is what the problem is asking for, the mass of hexane. Okay, so we can convert that using its molar mass. So we take the 40.33 moles of hexane, C6H14, and we're going to multiply it by its molar mass of 86.02 grams. Take that value, we'll multiply it by 86.02, and we get a value of 3,469.508 grams. Now our problem has 3 significant figures, so our final answer should be 3.47 times 10 to the 3 grams of hexane, C6H14, to account for sig figs appropriately. Okay, so that's a similar type of problem that we've been doing, just working backwards now. So we can use our known yields of specific reactions to find how much of our reactant we need in order to produce a certain amount of product. Okay, I want to put everything from this lesson together now with this problem here. So, potassium chloride is used as a substitute for sodium chloride for individuals with high blood pressure. Potassium chloride is made from a reaction between chloride gas and potassium, given in the balanced equation 2K plus Cl2 goes to 2KCl. The first thing we want to do is identify the limiting reactant and the mass of KCl produced when 10 grams of chlorine gas reacts with 14 grams of potassium. The second thing we want to do is determine what is the mass of the excess reactant remaining when those two reactants react together. Finally, if the actual final mass of KCl is 13.5 grams, determine the percent yield for this problem. So take a second and pause your video and think about how you would go about each one of these steps, and feel free to try to solve each of them on your own, and then come back and review the video as your answer key. This problem is a long one, okay, but it is one that brings together everything that we've talked about in this entire chapter. So, the first part is asking us to identify the limiting reactant and the mass of KCl produced. So, we're going to do like we did in the beginning of our lesson, and we are going to find our limiting reactant given our masses of our reactants. So, we start with chlorine gas. We have 10 grams of chlorine gas, and we want to convert that to KCl. You can either go to moles of KCl or mass of KCl. It doesn't matter. They're each going to tell you which one is your limiting. I personally feel like going to mass of KCl for each of my reactants. That way it answers the second question of this problem altogether. So that's just what I'm going to do. If you want to stop at moles and determine your limiting reactant from there, and then only do the conversion from moles of KCl to grams of KCl after you've determined that, go for it. It does the same thing. So we have 10 grams of Cl2, and we are going to convert that to moles of Cl2 using the molar mass of 70.9 grams. Once we have moles of Cl2, which we can calculate, I'm going to try to keep it small to use up my space properly. So we have 10 divided by 70.9. We get out 0.14104. That's moles of Cl2. We can now convert this to moles of KCl using our balanced equation. So for every 1 mole of Cl2, we create 2 moles of KCl. So we take that 0.14 and we multiply it by 2 to get out 0.28208. And that's moles of KCl, which I'm going to convert to grams. 1 mole of KCl is 74.54 grams. So we get out 21, here I'll put it in a different color, we'll do pink. 21.0268 grams of KCl. Now if you wanted to stop here for this part and then for the next part also stop at moles and then compare, you can. It's going to tell you the same thing. So we can then start with our second product, which is, or second reactant I should say, which is 14 grams of potassium. We'll do the same steps. 1 mole of potassium has a mass of 39.09 grams. We get that from the periodic table directly. So we get 14 divided by 39.09. We get 0.35814 moles of potassium. We then use our mole-to-mole ratios to convert from reactant to product. So for every 2 moles of potassium used, we get out 2 moles of KCl used. So we just get out 0.35814 moles of KCl. So again, if you didn't want to convert to grams just yet, you could see that this is a higher mole value than this. So that K is not going to be our limiting reactant, Cl2 is, but we can just finish out the problem. We know that 1 mole of KCl has a mass of 74.54 grams. So we multiply 4.54, and we get 26.6963 grams of KCl. So we can see from either the mole values or the mass values that Cl2 is limiting because it produced the lesser amount of product. It limited the amount of product that we can make, therefore it is the limiting reactant. Okay, so that's A. We found the mass of KCl produced as well as the limiting reactant. All right, here is our answer to that problem. Okay, here we'll erase some of these numbers for sig fig purposes. There we go. Okay. Our next question is asking us, what is the mass of excess reactant remaining when these two reactants come together? So we know that the maximum amount of KCl that we can form is 21.02 grams. We now want to determine how much excess reactant, how much K is left over. So for this problem, this is one that we can do 2 different ways. We can take our maximum amount of product, which is 21.02 grams of KCl, and we can convert that back to our excess reactant. So we just convert this to moles using the molar mass, 74.54. That's grams in 1 mole. We get 21.02 divided by 74.54. That's 0.28208 moles of KCl. We then convert that to moles of our excess reactant, which was the K, which is a 2-to-2 ratio, so 2 moles of KCl is 2 moles of K. So we get out 0.28208 moles of K that we need to use in this reaction. So finally we have to convert that moles of K to grams of K because we're only given the mass of potassium in this problem. So if I want to compare the mass of potassium, I'd have to convert that moles to grams. So we're going to take that 0.28208 moles of K and just convert that back to grams. So 1 mole of K is 39.09 grams. So oh, I have a typo. I did not copy from my calculator correctly. It's a small change, but you want to make sure that we are getting all these numbers perfect. And this is just coming down to rounding differences, sig fig changes, and everything like that. Okay, there we go. Now we can multiply by 39.09 times, there we go, forgot that part, 28199, and we get 11.0229 grams of K. Now this is the amount of K that was used up. Okay, that's how much I needed to produce 21.02 grams of KCl. Okay, I have some K left over. So what we want to do is take our initial mass of potassium, which was 14. I started with 14 grams. I only used up 11 grams, 11.02. We'll round it off for sig fig purposes. So the amount that's left over is the difference between those values. So we have 14.0 minus 11.02. So we have 2.98 grams of potassium left over. Okay, the next question now is asking us if the final mass of KCl is 13.5 grams, determine the percent yield. So the final mass of KCl that was produced is 13.5 grams. That makes this the actual yield. Our theoretical yield is the maximum amount of KCl that can be produced from our limiting reactant, which we already have from part A. So part A calculated our theoretical yield for us, meaning that the last part of this problem, C, all we have to do is take our actual yield, which is 13.5, divide it by the theoretical yield that we've already calculated in part A, and multiply that by 100. And we get out 64.2%. And that is our percent yield. So this problem nicely brings together all of what we've done in this chapter. We have a balanced equation using multimole ratios, using those multimole ratios to determine our limiting reactant and our theoretical yield of product, and then using that theoretical yield and comparing it to an actual yield of that product to get a percent yield of the reaction overall.